Yep.
Okay, my name is Infusino. I come from University of Reading, and I'm very thankful to the organizers because actually what I'm speaking about it's not exactly in polynomial optimization. I hope you can forgive me for that. But I work more in the setting of moment problem, and what I'm telling you today is about the realizability problem. That is a problem arising from many applications, from applied areas, and actually it's nothing else than an infinite dimensional version of the moment problem. So I would like to give you just a flavor of how this problem appears from applied areas, and then I will try to formalize mathematically so that it will be clear for everyone that it's actually a moment problem. And then I will just recall some basic results that I think everybody knows in this audience, and I will show you how the results in the finite dimensional setting can be connected with the infinite dimensional setting, and we can get our result, for semi-algebraic set actually of generalized functions. So the realizability problem arises in all the areas that deal with the analysis of complex systems. Complex systems are many body systems, so system consisting of a huge number of particles, and so the main difficulty in the analysis of this kind of system is that you cannot really describe the property of each component, of course. And for example, this kind of system are a fluid composed of molecules, a galaxy composed of stars, the nervous system in which there are different neural spikes traveling. So you see, in all this kind of system, you cannot really pick one component and so describe the properties of each of this component. And the common strategy that is used is just to focus on some global characteristics of the system and try to approximate these properties through methods like approximation schemes, statistical estimation, so that in the end you get a bunch of characteristics that you think are the characteristics that you wanted to approximate and to know, but actually you are not sure. And so you want to measure how good is this approximation. You want to know if these characteristics actually are compatible with the initial system. And this is the realizability problem. It asks if there exists a real state of the original system such that the characteristics that we predicted are actually the characteristics of the system. And let me formalize a bit mathematically this problem. And for this, I need the configuration space. Well, the concept is very easy. A point configuration is basically a collection of random points in the Euclidean space such that if you fix a compact volume, a finite compact volume, you find only finitely many points in this volume. So you can represent each point configuration as a sum of Dirac measures concentrated at some points of the space. And I will call gamma over T the set of all possible configuration, and of course they are a subset of the set of all random measures that I will indicate with R over T. And I call point process a probability measure on the configuration space. Okay, so coming back to reality, the xi that we found here, the masses of the Dirac measure are nothing else than the position of the entities of the system. So if you have a fluid, the position of the molecules. If you have a galaxy, the position of the stars. And here I listed only a few people that came up with the realizability problem in applied areas. For example, Stillinger and Torquato were analyzing heterogeneous material where it's difficult to understand the distribution of the matters, and so they were coming up with the realizability problem. And actually, one of the first papers about realizability problem is by Perkus that he was studying the mechanics of fluids. And in all these fields, the quantities that usually are analyzed are the correlation function. And usually the lower order correlation function, very often only the first two, because they represent the majority of the properties in which they are interested in. And just to give you, an intuitive definition of what is a correlation function, let's fix in our mind the example of a fluid. And the first correlation function is what is called the one particle density. So if you fix an infinitesimal volume of your fluid, the one particle density is the expected number of particles that you will find inside this infinitesimal volume. So if mu is the process that you have on your system, basically the expectation value with respect to mu of a configuration is what I call one particle density, so the first correlation. And the second one is the pair density, so the expected number of particles that you find if you fix two volumes, with one particle in one volume and one particle in the other one. And so if I give you a point process, in principle, you can compute what is the correlation function of any order. But actually, the problem is that the point process on the system is often unknown. And so, as I said before, there are many methods used like experimental measurement, approximation schemes, encoding of system properties, and statistical estimation to get value for the correlation. And so in the end, the problem is that you are given of two functions that usually are symmetric, and they ask if there exists a point process on the space of Wall configuration such that these two functions are the first and the second correlation function. So, as I said before, we can define the correlations like expectation of some special power of configuration. So let me define more precisely what I mean. So if you have a configuration, the end power is the usual product of measure. I mean, when you see the cross, I just mean the product of measure, that in the case of Dirac measure is just the sum of all possible indices of product of Diracs. And the factorial end power instead, that I indicate with the dot, is the sum over only over the distinct indices. It's called factorial because it's very nice, because if you plug in the a to the power n, you get just the factorial of the number of the measure gamma of a. And so, as I said before, the correlation function can be defined like the expectation of the factorial power. And instead, we call moment function what is obtained like expectation of the point process with respect to the usual power. Since there is a one-to-one correspondence between the two products, of course there is a one-to-one correspondence, as you see I did only for the first and the second order, between the correlations and the moment function. And so whenever I manage to resolve the realizability problem for correlation, I manage to solve it for the moment function. So for simplicity, for now on, I will consider only moment function because it's easier to work with the cross product. Okay, so we are ready to give the mathematical definition. And so I have a configuration, and I'm given of a function of n variables with compass support continuous on Rd in the n, and I can define this bracket between fn and gamma to the power n like the integral of the function with respect to the product measure. So in the case of Dirac measure, you see just the sum in all the possible value that the variable can assume. And now if I fix a subset of gamma over t, and I give you a sequence of moment functions that you obtain experimentally, well, the problem is, can I find the point process concentrated on this subset? With concentrated, I mean outside this measure is 0, such that the bracket of the function, the nth entry with a test function fn, is exactly the integral over s of this kind of generalized monomial that I defined with respect to mu. So actually, this means mn is the expectation value of gamma n with respect to mu. So is the end moment function? This is my question. And so now it's clear, especially after the talk of Professor Nee, that this is a moment problem. So I can be very fast on this, because the moment problem was, I mean, if you are given of a sequence of numbers and you fix a subset k of R, then you ask if there exists a measure supported on k such that mn is exactly the end moment. And the same you see here, because instead of numbers you are given of functions, actually of measures, and you ask if you can find a point process that is a measure concentrated on a subset S, such that this is a kind of generalized moment, let's say, of the process mu. Okay, so actually, the realizability problem is nothing else than an infinite dimensional moment problem, I mean, on an infinite dimensional space. Okay, and the connection between these two problems is very strong because, for example, you can project the realizability problem on an infinitely many moment problem, infinite dimension. How I do it? I mean, if you consider a projection map that is associated to a compact volume in RT, the projection map is defined such that if you have a configuration gamma, you can associate the value of the measure of the compact subset with respect to gamma. So if I give you a measure that takes, I mean, with a measure on Rdn, and I fix a compact volume, I can always associate the number that is given by the measure of lambda to the power n. And so it's quite easy to prove that if the realizability problem is solvable on some subset S, then for any compact that you can take, the associated sequence of numbers is realized, so the moment problem of the associated moments is realized by the push-forward measure on the image of this subset. So just to fix the ideas, if I can solve the realizability problem on the set of all random measures, actually I can solve the moment problem on R plus for the associated moments. If I can solve it on gamma of RT, I can solve it on N0. On the set of all probabilities, I can solve on 0, 1. So with this, I simply mean that that we have an infinite range of moment problem in finite dimension associated to each realizability problem. Okay, and so the moment problem actually can give necessary condition for the realizability problem. Okay, so let me recall some definition. I will be fast because Professor New already gave. Okay, there is functional associated to a sequence. It's just the functional that takes one polynomial and substitute the value obtained replacing each of xn with the nth entry of the sequence. And so an easy computation tells you that if you can solve the moment problem on the set k, you can write the Ritz functional like the integral over k of the polynomial p with respect to mu. And so whenever p is non-negative on k, you get that the Ritz functional is non-negative. So basically, the non-negativity of the Ritz functional on k is a necessary condition, but actually it's also a sufficient one, and this was proved by Ritz for one dimension and by Haviland for dimension greater than 2. And this is a beautiful theorem because it solves the moment problem for all compact, or closed subset over D, but actually it's not so practical because you cannot really check, and everybody knows in this audience how difficult it is to find out which are the polynomials that are non-negative on a subset. So, in some cases, this is easier, this abstract condition becomes more concrete, and this is the case when you have some kind of Positivstellensatz. So, I mean, when you can split, actually, each polynomial like sum of squares. And, I mean, this theorem, on R, for example, a polynomial non-negative on R, everybody knows this can be written like sum of squares, and so it's very easy to see that if you compute the Ritz functional of the polynomial, you can write down like the sum of the Ritz functional of two squares. And so using the Ritz-Haviland theorem, you can prove that the moment problem is solvable on R if and only if the Ritz functional is non-negative over all the squares. And if you assume also that this kind of restriction on the growth of the moment is true, this is called Kahneman condition, and Kahneman proved that in this case the measure that solved the moment problem is unique. This kind of condition, I mean, are kind of positive semi-definite condition, and they are called like this because if you consider the Hankel matrix, the matrices of them associated to a sequence in this way, I mean, the condition that the Ritz functional is non-negative over the squares means exactly that every Hankel matrices of any order is positive semi-definite. So whenever I will say that a sequence is positive semi-definite, just keep in mind that I mean or that all the Hankel matrices are positive semi-definite or that the functional is non-negative on the square. Okay, as I said before, I was interested in the moment problem on basic semi-algebraic set and that are defined just like sets that where finitely many polynomials are non-negative. And these results was one of the first that I knew about the moment problem on semi-algebraic set, and is due to Bergen-Masaryk in 1982, and states that if you have a K basic semi-algebraic and compact, then the measure realizing the moment problem is unique if and only if the Ritz functional is non-negative on the squares, and on the squares multiplied by the polynomials defining the semi-algebraic set. Actually, the condition of the compactness guarantees that the sequence satisfies the Kahneman condition, and so again, this guarantees the uniqueness of the measure. So again, as we saw before, you can state the moment problem in more dimension, and here you are not so lucky, we don't have the same theorem of Hilbert, was known already to Hilbert, that it's not true. Sorry, that every polynomial non-negative on Rd is sum of squares, but actually using tools from spectral theory, it's possible to prove that if you assume this kind of condition that is called, I mean, we can call multivariate Kahneman condition, then, well, you have a kind of analogous of Hamburger theorem also in more dimensions. Okay, but this for RD. So what is known about semi-algebraic set of RD? Well, I mean, the definition is exactly the same, and I define here the preordering associated to K and the quadratic module associated to K, and usually it's easier to deal with this kind of cones because you can check by semi-definite program that a polynomial is inside one of these two cones, and and also, let me define that a quadratic module is Archimedean if there exists a natural number such that n minus the norm square of x is inside the quadratic module. Okay, so we already heard about these two results by Schmidtgen and Putiner that basically solve the moment problem on K basic semi-algebraic compact subset over T, and they characterize actually the solvability of the moment problem through the non-negativity of the Ritz function on the preordering or on quadratic modules. And actually this result of Putiner generalized somehow the one of Bergen-Masaryk. And, and many people in this audience studied the problem of considering K basic semi-algebraic sets that are not compact. And here the problem of solving the moment problem is actually strongly related to analyzing the closure of the preorderings and the quadratic module with respect to the finest locally convex topology that you take on the space of polynomials, and the relation between this closure and the cone of all positive polynomial or non-negative polynomial on K. And but all these results that I stated here, they show that actually the solvability of the moment problem via preorderings and via quadratic modules, this is possible only for specific class of semi-algebraic set. And one of the recent ideas that actually was of inspiration also for us in our infinite dimensional setting is this one developed by Gassemi, Coleman and Samay, and by Lasar, and that basically they considered the Ritz functional, they assumed the continuity of the Ritz functional with respect to a topology which is not the finest locally convex topology, but other kind of weighted norm topology. And I will just say this result, just cite this result of Lasar, that basically considered a K basic closed semi-algebraic set in RT, and he assumed that the functional LM is LW continuous, that I define in 1 second, and this guarantees that the moment problem is uniquely solvable on K if and only if the Ritz function is non-negative on the quadratic module associated to K. And this kind of LW norm, basically it's a restriction on the growth of the moments, and is a kind of L1 weighted norm. And in particular, this condition that, I mean, looks quite simple, but can be written even much simpler in this way. And, and you can see, I mean, that this kind of bounds here implies the multivariate Kahneman condition that I stated before. So actually, I can also rewrite the theorem in this way, just assuming that if this bounds is true of, on the moments, then the measure which solves the moment problem is unique, and the condition that the Ritz function is non-negative on the quadratic module, I can rewrite a bit more explicitly, and it's exactly this, that the Ritz function is non-negative on the square and non-negative again on the square times the polynomial which define the semi-algebraic set. And so now let's go to infinite dimension. What happens in infinite dimensions? Actually, we have kind of analogous theorem, because if, again, the Ritz functional can be defined in the same way, but this time we don't have any more polynomial in real variables, but we have polynomials in this generalized form. You remember the monomials I defined before, like the integral of the function an with respect to gamma to the power n. And again, the Ritz functional does the same. Substitute to the powers the nth entry of the sequence, nothing of special. And Lenard in 1975 proved that if you have a subset of the set of all random measure closed with respect to the vague topology on R over T, well, the sequence, given a sequence of measures, you can realize on S, so you can solve the moment problem on S, if and only if the Ritz functional, defined in this way, is non-negative over all the polynomials that are non-negative on S. But again, like the Ritz-Avilan theorem, this theorem is not so applicable. I mean, the conditions are not so checkable, because if it's already difficult to find out which are the polynomial non-negative on a subset of Rd, imagine on a subset of infinite dimension. And so, I mean, there is a huge literature about finding positive semi-definite condition also in this infinite dimensional setting. And I mean, here there is literature by Berezovsky, Kondratiev, Kuna, Litinov, Limay, and Oliveira, and basically they were starting with a sequence of correlation function, and all the theorems that are in these papers are of the form: we assume a restriction on the sequence that we are given, and we find condition for the realizability in terms of the non-negativity of the Ritz functional, and plus positive semi-definite condition. So actually, they don't get rid of the non-negative, I mean, of the problem of characterize all the polynomial non-negative on a subset of configuration space, of random measure, or whatever. And a very general version of the Hamburger theorem, but in infinite dimension, was given by Berezovsky and Kondratiev in 1988, and they consider a very general setting, the setting of nuclear space. So basically, they consider a space that is a projective limit of a sequence of Hilbert spaces, and they consider the dual with respect to projective topology, and then they take just the tensor, like the projective limit of the tensor of each of the Hilbert space. And basically, they stated the moment problem in these terms. If you are given of a sequence of functions that are inside the dual of the tensor, a symmetric sequence, they ask, does there exist a measure concentrated on the dual such that for any test function that I take in omega to the n, to the tensor n, I get exactly the relation that we saw before. So basically, they stated the moment problem on nuclear space. And what they found out that if you assume the positive semi-definiteness of the sequence, so you assume that the Ritz function is non-negative on the square of this generalized polynomial, and you assume this restriction that, as you can see, is very, very similar to the restriction that I showed in the Lasserre bound that was assumed, and I call this kind of restriction be determining because the moment problem is determined, so the measure is unique. Then they proved that actually, if you assume this bound, then the sequence, if the sequence is positive semi-definite, if and only if you have that the moment problem is uniquely solvable on omega prime. And so our idea was exactly this one. We took the result of Berezovsky and Kondratiev that is very general and abstract, and we decided to apply this to the set of all generalized functions, d prime, the dual of the function infinitely differentiable with compact support. And we took the ideas coming from the Lasserre theorem, and we managed to prove an analogous of the Lasserre theorem also for semi-algebraic subset of d prime. And actually, this result solves the realizability problem on a lot of sets, not only on the random measure, on probabilities, on the configuration space. So whenever you can write down a set, like semi-algebraic set of d prime, of the generalized function, for this reason we chose this very large space and very general space, because we can include many of the examples that comes from people in application. And so basically we took omega equal to the space of all infinite differentiable function with compact support continuous, which is nuclear by a result of Berezovsky of 86. We took the dual, and we made the dual with respect to projective topology, because in the theorem it's required that you have a projective limit of Hilbert space, and actually you can write down this space like projective limit of Sobolev space, weighted Sobolev space. And now a semi-algebraic set is just a set given by, again, finitely many or infinitely many polynomial constraints. So we don't need necessarily that this subset is countable. And we define the quadratic module in an analogous way of the classical one, And we just assume by simplicity that you always have 1 inside. I mean, so you always get the condition of the non-negativity of the squares. And so our result states exactly that if you have a sequence of functions, generalized function, symmetric, and you assume the bound I showed you before, then what you get there exists a unique process realizing the measure on this given subset if and only if it's non-negative on the quadratic module. So exactly the analogous of what we have in finite dimension.
How do you apply the distribution to Pj? Well, Pj is a polynomial, right?
Yes, exactly.
But it doesn't have compact support.
Sorry?
I mean, gamma...
Oh yeah, you can do a kind of limit.
Kind of limit?
Yes, no, it's basically you... Okay, I understand your problem, but I mean, you can, since this is the projective limit of this subtle space, so you basically, when you're going to consider this, you consider the polynomials here, and then you do the projective limit and... Yeah, exactly, yes, it's like this, like a smooth cutoff of... And yes, basically the main difficulty in the proof of this theorem was exactly dealing with the polynomials that are not necessarily continuous with compact support, and all the topological problem coming out from the fact that you consider the projective limit topology, and so on the dual you have the weak topology, and so you don't have always the regularity of the measure, and this, but I don't think I have time for the proof. But what I want to say is that this theorem that looks very general, in reality managed to give results also for application, because, for example, you can write down the set of all random measure like semi-algebraic set, because just you have this kind of, let's say, monomial of first degree, infinitely many. And so what you get that you can check concretely if these conditions are satisfied, because these are just like infinitely many inequality. Now I know they are infinitely many. This is the problem, because we were studying only the full realizability problem. And actually the main question is find out if we can solve also the truncated realizability problem. And there is already some work coming from people working in statistical mechanics. Joe Lebowitz and Spear and Kuna proved the theorem where basically they solved the truncated realizability problem, but on very specific set. And again, only involving the non-negativity of the functional on all non-negative polynomials. So again, the conditions are not so practical. So we hope that with our theorem that involves semi-definite condition, we can manage to solve also the truncated case, and maybe to find out, I mean, to reduce the number of the conditions that you have to check. Actually, this is possible, for example, in the case of configuration, because if you have the space of multiple configuration, with multiple configuration, I mean configuration that can, you can allow two particles to stay in the same position. And this can be written like semi-algebraic set, but the condition that you get, as you see, is on polynomial of arbitrarily large degree. And so, I mean, this is not optimal. And so, but if you restrict your attention to the simple point configuration that are actually the one that you, in reality, you have more often, we managed to prove that, I mean, with a corollary of our theorem, we can reduce actually the condition only to the first 2 degree of, you see, you don't have to control all the degree of the polynomials, but only the first 2, but you have to, I mean, the price you have to pay is that you have to assume another condition, another restriction on your initial moments. Okay, thank you very much for your attention. Any question, comment?
You had several degrees of generality. Finitely supported measures, random measures, and then distributions.
Yeah.
So there was a result for distributions, and there was not really any result for
the measure, you mean?
For these 2 other cases.
No, I mean, but these are subsets of generalized functions.
Yes,
so
I mean, but probably one would have some more specific information for finitely supported measures or for random measures.
Okay, yes, but I mean, the random measure, this is solved for the random measure, because you can write down like semi-algebraic, and so you just apply the theorem.
Okay.
So for the configuration, it's again the same.
Random measures and distribution case is more or less the same if you want to consider non-negativity.
Exactly, yes. No, but you can get the condition with semi-definite. Just the important is that you manage to write it down like semi-algebraic, and then you get all the support you want. This is, I mean, for example, also for the probability. If you have the set of all the probability, you can write down like semi-algebraic set of the generalized function of the distribution, and then again you can apply the theorem. I don't know if okay, so I guess we can